Hi everyone, my name is Samuel Jackson and I'm from Thomas Jefferson Charter School, and that is in Caldwell, Idaho. So today I'm here to talk to you guys about the Mass Spectrometry, or as people call it, the Mass Spectrometer, or the Mass Spectra, or the Mass Spec. So there's many different names that people can call it. But before we start, we need to talk about terms that or vocab that you need to know about to listen to what I'm saying. So first thing is about mass. So I don't talk about mass a lot, but it's important to know what mass is, okay? So a lot of people get mass and weight mixed up. So a mass is how much is in an object, okay? So this is not like if you say something is 2 pounds, it's not the mass. That's the weight of an object. Next, we need to talk about electrons. Through school and through all your sciences, you've talked about atoms and molecules, but also you need to know what electrons are too. Electrons are kind of hard to understand, but not too hard. So electrons are the negatively charged particles in an atom. So, as a lot of people know, that there's the positive charge and negative charge of an atom, and the electrons are what brings the negative charge of an atom. So, that's the electrons. And next are ions and cations. So, ions are the basic of it. But then you also need to know what cations are, because I talk about that a lot. So, an ion is when an electron is taken away or added to an atom. So, you might be asking, what does this do to an atom? So, electrons are taken away. Well, this is very important to know, because if an electron is added to a particle, it becomes negatively charged, okay? But, and this is where cations come in. So, if you take away your electron, you're giving a positive charged. You're making the atom positive charge. Well, that's the basics. And now, what is the mass spectrometer and how is it used today? So the mass spectrometer is a big machine that people use to determine what's in a chemical, what's in a poison, or basically what's in something. And so they have to put in this machine and it calculates this whole thing for them. It's really nice. And what do they use it for today? Well, they use it a lot in chemistry or forensic science or a lot of other sciences as well. They use it, as I said, to separate the ions in a chemical. So it's very important. So now let's talk about the machine. So this isn't what it looks like on that side. It's actually a big machine, and it's going to be shown. So as you see, this machine is big. And this is the inside, what is inside the machine. And this is what makes it all work, okay? So first, you need to start with your source, or your sample. So your sample is basically anything. And so, for example, it could be, let's give the example of carbon dioxide. It's a simple one, because it's this 3 atoms, CO2. So it's one of the simplest ones you can do. So it goes to sample, and these samples are very small. It has been said that these samples are smaller and less dense than the atmosphere, okay? So then it goes through this tunnel, so it goes to a finer beam, and then it goes to your ion source. And this ion source, people say, is the heart of the machine, okay? And people also call it the repeller electrode. So this basically makes your beam go even smaller. You can't have this machine if everything's spread out and you can't tell where everything was. So it has to be in a small beam to go through the process. And after it escapes the ion source, it goes to the filament category. So the filament is basically a wire, it's kind of like a wire that is heated. It's heated, and it has electrons, and these electrons get heated up, and they want to attack these ions because, oh man, they're in their space. They want to take the space back. They don't like ions in their space. It's their territory, so they go attack it, and this attack of the ions makes ions be cations again. Well, be cations. It's not again. Just be cations. So then when it escapes this, there's different particles. So right here, there's the bluest extra electrons have been out now, and the red are now the cations. So now it then goes through the acceleration slits. So those acceleration slits speed up the process, okay? You can't go through this process with it being slow because it's going to have a hard time going through the magnetic field and getting your source. So it speeds up the process, but speeding up this process adds another ion to it. This ion is the extra ions that you don't want, such as CO2. Let's say you want the carbon and not the oxygen. So this extra atoms are now the carbon, and now this is the this is the carbon. Now that's the oxygen. So then it goes to your magnetic field. Okay, so this magnetic field depends how strong it is. You put it how strong you want, like depending on your ions you want out. So you adjust it to the light ions because light ions are easier to pull away, okay? So it pulls away the light ions and the heavier ions and makes this focused ion beam. So this focused ion beam are your ions you want. So then it goes through the detector, which calculates mass to charge, and I'll explain that ratio later. So this mass to charge then goes to your computer and graphs it. This graph can go up from 100 to 0, depending on how much charge it is. Okay, so now let's talk about the ratio. So this ratio is mass to charge, okay? So when it goes through this process and becomes a cation, as everyone knows, as I said earlier, cations have a positive charge. So depending on the charge, you kind of want the least amount of charge because it's easiest to deal with, but there's many different charges. So let's go with CO2 again. So carbon dioxide has a AMU, so atomic mass unit, of 44, okay? So this is your mass now, okay? So this is your mass, okay? So let's say you can't get a 0 charge because that means it's a normal ion. So you want it to be a positive charge. So let's say it has a 1 charge, okay? So that 44 divided by 1, because you can write mass divided by charge to mass divided by charge, like that. So this would equal 44. So you graph this to 100, but the max for this is 44, so you're going to go to 44, and you're going to graph it. Okay, so this, oh, that was a stupid line. Okay, so this is called your baseline, okay? So this is the base, so nothing can go past this point, okay? But now let's say you have more than a 1 charged ion. So let's say you have a 2 charged, okay? So this means your ion is doubly charged. Oh. Now your calculation is going to be 44 divided by 2, so it's going to get a 22 ion, okay? So let's go to 22 and graph that. So as you see, this did not go past 44 because that's the base. That's going down to 22. Now, let's say it has a 4 charge. So now it goes 44 divided by 4 because the 4 charge, and that's 11 charge. So you do 11, well, so 11, so you go up 11. So that's the graph. But these graphs can vary. And they're normally always put into a bar graph, but not always. Some people don't like bar graphs, so they don't use them. So, but these, it doesn't always go to an easy number to divide it. It could go to 0.5 or 0.25 or 0.75 charge. So it just depends on the ion. And next, so lastly, I want to talk about when can we see this in real life? So this is used in crime shows all the time. Okay, so if if they show the forensic science side or any of the science side to a crime, they normally use this machine. So this, such as NCIS. NCIS uses this machine a lot. When Abby says, let's put this through the mass spec, that she's meaning this machine. Let's put this through this machine to get what ions are in the body or something.